Okay, here we are for the second part of, so you still need to watch this one before you do the homework for Thursday, the second part of section 4.4. So we're going to go through just a couple more practice problems. One is taking the integral of an absolute value function. So you should know that absolute values by definition, you can split this up. So when I have the 0.1 half here, so 2 times 1 half is 1, right? I have 1 minus 1, which is 0, and that's a place where an absolute value function is not continuous. So this function is not continuous over the whole interval 0 to 2. And so when you are integrating, taking the definite integral of an absolute value function, you need to split that function up, right? So if you think about like an absolute value function looking like this, not necessarily this one, but well, yeah, something like this, you're going to integrate this over the range that it is continuous for, and then this over the range that it is continuous for. So by definition, so if this one, 2x minus 1, 1 half is kind of that magic number where it's equal to 0. So you should know from before I came into the picture that this same thing can be defined as being equal to negative 2x minus 1 when x is less than 1 half, and 2x minus 1 when x is greater than or equal to 1 half. So when we are integrating absolute value functions, we're gonna split it up to deal with each of these functions at the appropriate range. So this thing becomes negative 2x minus 1. I'm going to integrate that. And so this is valid when x is less than 1 half. So I'm going to take it from 1 half, from 0 up to 1 half. And then I'm going to add to that the integral of 2x minus 1 with respect to x from 1 half all the way up to the end of the range, which is 2. So this is an example of that additive property that I had up before. This, I'm still integrating from 2 down to 0 in the end, right? I'm just splitting it up. So I'm going 0 up to 1 half because this is true in that range. And then I'm going from 1 half up to 2 because this is true there. And so then when I integrate it, this is, so negative 2x really becomes, I'll rewrite it so it makes sense what I'm saying. This is negative 2x plus 1 when I distribute that sign. And then this stays the same. I'm running out of room, I apologize. Okay, so hopefully you can read that. So if I come over here and integrate that, negative 2x becomes negative 2x squared divided by 2 plus 1, which is plus x. And I'm going to evaluate that function from the point 1 half down to 0. And then I add to that the second, the derivative of the second part of the function is 2x squared over 2, I divide by the new power, minus x. And I need to evaluate that from 2 down to 1 half. And so when I put the numbers in, this ends up being negative 2 times 1 half squared over 2 plus 1 half minus, when I put 0 in, it's just 0 for everything, plus 2 times 2 squared over 2 minus 2. And then I need to, I'm running out of space. I put the 1 half in, plug and chug, well, 1 half in. And so when I put all those numbers in, so just, I hope you could handle that because you're just plug and chugging. I end up getting 5 halves as my answer. And so that is how you would take the definite integral for an absolute value function. So those are the ones where you need to split them up and use that additive property. Another way a problem might ask a question, or yeah, question you, is by asking you to find area, which is really asking you to take the definite integral. So there's one in your textbook. I'm still following along with PowerPoint. And it says, I can't even read because it's so small. Find the area of the region bounded by the graph of y is equal to 2x squared minus 3x plus 2 on the, and then it's bounded by the x-axis on the bottom and the vertical lines x equals 0 and x equals 2. So what this is asking me is, so if I graphed this function on an xy plane, I don't know what the graph looks like exactly, but here I have this function. It's asking me to find the area that's bound by that curve, the x-axis, and then the vertical line x equals 0 and x equals 2. So this stuff right here, that's what it's asking me to find. So how do I do it? The area would be equal to the integral from 2, or 0 up to 2 if we say it that way, of this function. It's the area under this curve. So 2x squared minus 3x plus 2. And I'm going to integrate that whole thing with respect to x. So, which hopefully now you could solve, but when they ask me area questions, that's what they're asking me to do. So if I integrate this, let's finish it off. This becomes 2x cubed over 3 minus 3x squared over 2 plus 2x, and I want to evaluate that from 2 to 0. At 0, it's just 0 because everything has an x in it. And so when I plug values in, this ends up being 10/3. So I just put a 2 in everywhere, and that's my area. Okay, so there's one other new concept I want to get into. You're not really going to see it on the homework until till the set that's due next week, but I thought I'd introduce it to you now. And that is finding the average value for a function. And you use the mean value theorem to do that. Now, I had mentioned, we learned a little bit about, and then I sort of dropped it, the mean value theorem with differentiation. So the mean value theorem is very useful with integration. We're not going to see, just because of time, we're not going to see most of its uses, and I'm not going to prove it. In fact, it's pretty difficult to prove. So not even your textbook does it. So it seems not to be first year calculus stuff. But the mean value theorem states this. So just bear with me for now. So for the definite integral, as shown, there is a value, c, where f of c times b minus a is equal to the definite integral. So that's kind of totally abstract. Like what is what's that even saying? What is important, I'm just going to jump down to it, is this quantity is the average value for a function in the interval a to b. So if I have a function, let's just say a simple function, x squared, and I want to look at it in the interval 0 to 4, I can find the average value of that function in that interval if I use this mean value theorem. So if I take this and I solve for FC being that average value function of the function, then I can say 1 over b minus a, I'm dividing both sides by b minus a, times the definite integral of the function would give me the average of that function. And so I will own, just watching time and don't have much space, sort of waving my hands at that. But if you accept, you can go look up proofs if you would like, but if you accept that this is the average value for a function, this is a really easy thing to find, just the difference between the two values of the interval. And then we now have mastered, I hope, evaluating and finding the definite integral, and so we can find the average value of a function. So as an example, they say, oh my gosh, I cannot read my own writing. Find the average value of the function f of x is equal to 3x squared minus 2x over the closed interval, or on the closed interval 1 to 4. So they want me to find the average value of that function. And so since it's not a linear function, right, it's not like you can evaluate it at the two endpoints and divide by 2. So that's why you can't use 2.5 in there. So I'm going to use what I got from the mean value theorem to find the average. So the average for this function is equal to 1 over b minus a times that definite integral. So for this particular function, it's 1 over 4 minus 1, which is 3, times the definite integral from 0.1 to 4, 3x squared minus 2x with respect to x. So this becomes 1/3 times 3x squared becomes 3x cubed over 3 minus 2x. This becomes 2x squared over 2, and I need to evaluate it from 1 to 4. The 3's here cancel, the 2's cancel. I plug in my different values. So I'm going to plug in a 4, then I subtract when I plug in a 1. I'm just running out of space, so I'm not doing that. And I get an average value of 48 over 3, which actually happens to be a nice whole number, 16. So 16 is the average value for that function. So we'll see, again, more with that next week, but I just sort of wanted to introduce that and let you see it. And then we'll use that to move into our next, there's a second fundamental theorem next week, and that'll be our sort of grand finale of calculus.
Bye! Hope you learned!